This is the Algebra version A worked solutions. We are starting with graphical representation. First off, we've got a picture of an exponential graph showing how the sample changes with time. We are told that y is the number of bacteria and x is the time in hours. The function used to produce this graph is an exponential function, so it's an exponential graph. We are told what form the equation takes, and we are told that a and k are constants. A constant is a number, and so we're going to have to replace that with a number at some point. We are next told that the equation can be rearranged into this form. So we have to start with our original equation. Where are we? About there. So start with our original equation where we've got y equals a, b, k, x. And then we can learn both sides. So we get ln y equals ln a e k to the x. We can then separate these two. So we've got ln a plus ln e k x. And then we've got ln a plus, and the ln and the e cancel, just leaving us with kx. So what we've got is the equation that we're asked to find. Things that are useful to know about this equation: it's going to be the equation of a straight line. So if you think about it logically as a y equals mx plus c equation, we've got a value of y, or the thing on our y-axis. Then we've got the thing on our x-axis, which happens to be x. So k is going to be our gradient, and ln a is going to be our intercept. So, complete the table opposite, giving answers to 2 decimal places. Normally we're asked for 3 significant figures, but in this case we're looking at 2 decimal places. So, the table that we've got. If on our table function we put this in as ln x, and then looking at this, we've got all of the values that we want. So first off, we can put in 8, then 14, then 24, then 40, then 67, then 113, and that's got to the bottom of the table as it's currently written. So to 2 decimal places, we end up with 2.08 with rounding, 2.64 with rounding, 3.18, 3.69, 4.20, 4.73, and then lastly 1.1 is 5.22. So we can then plot those on our axes. If you look at the axes, we've got x on the x-axis and ln y on the y-axis. So we are going to be plotting this row and this row. Okay, so once the table's filled in, we can plot our points. In this case, what you'll find is the 14th point won't actually fit on the graph, but that's not a problem. So plotted the line, and we're asked to draw a line of best fit. There is a slight cheat with this one, in as much as if you go into the stats mode and then put in all of the data points, you can actually calculate the regression of a line in the form ax plus b, and it will give you a value for the gradient and a value for your intercept. So although you do have to still calculate it, you at least know that you're in the right sort of area. So we know that it should be, roughly speaking, y equals 0.263 x plus 1.58. So what we can do is, looking at our grid, we've got this point here. Nope, concentrate. 1.58, we've got this point here. And so if we take that through, then we can get a line of best fit. So working out the gradient, we have an intercept that equals, if we'd been working out on the calculator, we got 1.58, but in reality, we'd probably round it to 1.6. And we've got a second point that is taken that is quite far away, because this improves our accuracy. And our second point is going to be this one here, because it goes right through the middle of it. So that's going to be 12.473. So to work out our gradient, we have m equals, and it's y over x, so this is our second y, so we go 4.73, take 1.58, and we divide that by 12, take 0, and then hopefully we'll end up with something that is a lot like this. The reason for doing it, the reason for calculating it, is purely and simply just so that you've got a good idea as to whether or not you're right. And we divide that by 12, and we get a gradient of 0.2625. We've got our intercept that's coming in here. So we've drawn our line of best fit. So we plotted it, we've drawn a line of best fit, and now we use our line of best fit to estimate values for this and an equation y in terms of x. So we've just worked out what k is, because k is our gradient. And then the next thing we need to do is work out what A is. So we know that ln A equals our intercept, which was 1.58. So A will be equal to e to the power of 1.58. So A is going to be equal to e to the power of 1.58. So A equals 4.85. So we've now got a value for K, we've got a value for A, and we've got our original equation. So we've got our original equation. So we can now write this as y equals our value of A, e to the power of our value of K, so 0.2625 x. Okay, so 1f we've been asked to state the initial number of bacteria. So the initial number would be when x equals 0, when x equals 0, xk equals 0, e to the power of 0, anything to the power of 0 is 1. So our initial value will be A, which is why it's only asking us to state it rather than do anything with it. So initial number of bacteria is going to be 4.8. Now 4.8 sounds a bit weird because you wouldn't really get 0.8 of a bacteria, but this is being measured in thousands, so you can get 4.8 thousand. Okay, then we have a comparison. So number of bacteria in another sample. So this is a different equation. So we want to find the number, or find the time when the number of bacteria has doubled. So given that it's got the same rate, what we can do is we know that our initial value is going to be 5. So doubled is going to be 10. So what we can do is we can substitute this in. So we get 10 equals 5e 0.4 x. So we've got a 5 and a 10. So if we divide both sides by the 5, then we've got 2 equals e 0.4 x. Then we can ln both sides, so we get ln 2 equals 0.4 x. And then if we divide both sides by 0.4, then we get a value of x equals then 2 divided by 0.4. So that should be 1.73, and we are measuring this in hours. In exam speak, hence means use what you've just done. So this section, so hence write down the equation of the curve. So equation of the curve, we are going to need to know, we are using this equation and we are substituting in the values that we know. So we know that it's going to be a y equals graph. We know that our amplitude is 20 and that it's going to be sine, and then we need the angular frequency with t. So A and W, or A and omega, were our constants, and so they are the bits that we need to find values for. Okay, so we're now asked to find the gradient of the curve at the time when t is 0.00003. So, on our graph, find the point for 0.003 and draw a tangent, because you can only find the gradient from a line if you're doing it manually. So it looks like it goes through these 2 points and they're fairly far apart, so we've got slightly more margin for error. So our first point is at 0.0002 and 20, and secondly at 0.0004 and minus 20. So if we put that into the equation for the gradient, then we get about 200,000. If you put it into your calculator, you can ask your calculator directly for the gradient. It's the differential and is this third column here. To turn the derivative on, you do shift, menu, and then if you come down to derivative and put it on, it'll give you the gradient. If you leave it off, it'll take it off again. So if we put in our first column 0.003, 0.0003, then we've got our x value, and you can see it gives us a value of minus 2e5. That's fairly meaningless. However, if you go on top of it, it tells you that the exact gradient at that point is minus 209,000. So actually being 9 out when we're dealing with 200 isn't actually that bad. Just gives you kind of that reassurance that you're on the right lines. We're then asked for the meaning of the gradient. So our gradient is going to be telling us something. This axis here is the loudness of the note, and this axis is time. So our gradient is going to tell us that the loudness of the note is decreasing because it's going down by 1, 2, 1, 2, 3, so 200,000 decibels, so dB per second. Okay, so our last question is about transformations, and often they give you a slightly different equation for this. And that's purely and simply because if you've made a mistake with working out your own equation, they don't want to penalise you twice. So we are looking at going from y equals sine t onto y equals 60. So that bit's different between these two, and this big number here is different. So this 60 is not in the brackets with the x, so that is going to, and it's multiplied, so it's going to be like 60 times sine. So that tells us that we have we have a stretch scale factor 60 or times 60 in the y direction, and this big number here is grouped in with the x or the t, so that will give us a stretch scale factor times by, now it's in with the x, so it does the opposite of what you expect it to. So it would normally be a times, but here it's going to be a divide, and that's in the x direction. Okay, so looking at the profit section of the datasheet, we've got an average weekly profit, which is being measured in pounds, and we have a unit price, also measured in pounds. So we've got our equation. So the maximum average weekly profit, if we put this into our calculator as a graph, then we have minus 20 brackets x squared minus 70x plus 600. So our view window, there is no point in going below 0 for x, because you wouldn't be giving away your dance shoes, and a maximum value, if we put it as 150 initially, we should have a fairly good bet as to what we're looking at. You'll see it's fairly squashed down the front, so if we do view window and go down to 50, if we can't find where it is, then if we try zoom auto, then it gives us what it thinks its best guess is going to be. From this we can see where the maximum is, so if we use gsolve max, then we have an x value of 53 and a y value of 12500. So we want the average weekly profit. So our average weekly profit is on our y-axis, so that is going to be £125,000. And then we want the unit price. So the unit price at the maximum So we've got a II, and that gives us a unit price of £35. We've then got this. Now, hence basically just means use what you just did. So we've got to write the model in this form. So we've got y equals, and here we've got this value, which if you expanded it would be in front of the x squared. So that is going to be minus 20, same as it was in the first bit. Then we've got x minus, and it's going to be a squared thing. So the thing that is going in with the x is the x coordinate, and the thing that's not in with the x is going to be the y coordinate. So that is going to be our 125,000. So 1, 2, 5, 1, 2, 3. Realistically, you're going to want to write that a little bit more spaced out. So, by forming and solving a quadratic equation in this form, where A, B, C constants, so that means that A, B and C are numbers that you can find, then we want the cheapest unit price, which gives profit of this. So if we take our original equation, then that would be y equals this, and we want a profit of this, so it gets written as 10, 1, 2, 3. Now, practically, it makes more sense to use this equation rather than the one that you wrote, because this equation you know is right, and this equation you kind of hope is right. So we have minus 20 x squared minus 70 x plus 600. So if we start to rearrange that, we can divide both sides by minus 20, which means we end up with minus 5,000 equals x squared minus 70 x plus 600. If we move this over to the other side, then we end up with 0 equals x squared minus 70x plus 5,600. So we've got our first mark for substituting in the 10,000 from the profit. We've got our second mark for rearranging it, so it's an equation with a 0. So our last bit that we're going to have to do is calculate this value. So from a practical point of view, what we can actually do is go gsolve xcal when y is 10,000. So we have our first answer of x equals 23.82, and because it's money, we're going to need to get this in. So we have x equals 23 pounds 82p. And then if we move it across to the other side, then there's another time here. Now our question says find the cheapest unit price. £46 is quite a lot more than £23, so this one's going to be our cheapest. There is also likely to be another mark for putting your equation into the normal quadratic equation and substituting in there. Okay, so for part B, average weekly profit made by selling another brand. So another brand of dance shoes is going to be another equation. So we have our new equation. So list the transformations which map the graph of y equals x squared onto this. This is traditionally a different equation to the one at the top, or the one that you found out, purely and simply because what they want to do is not penalise you if you've got an equation wrong earlier on. So we've got 3c. If we deal with the x's first, we've got no stretch because there's nothing times by the x, but we do have this minus 25. So minus 25 is going to be a translation, and if we write that in vector form, because it's in with the x, we change the sign. Now the y one is this 4,000, because this is outside, so isn't going in our x direction, and is in the direction that it's implied, so this is positive. We've also got a stretch. We have this multiplication here, so we have a stretch, scale factor times by minus 10, and that's not in the brackets with the x, so it's going to be in the y direction. Moving on to section D with steel beams, we've been told that we have a solid steel beam with a width of 20 centimetres, supporting a load of W newtons. We are given that the maximum deflection is y meters, and we've got a formula. So L is the span length in meters, E is Young's modulus, so for steel this is going to be this. A is the area moment of inertia of the beam, so we're told for a beam with 20 by 20 square cross section, which is what this one has. Ooh, missed. We've got a value here. So W, E and A are constants. They are numbers. They may be numbers that you're given. There may be numbers that you've got to find, but they are going to be numbers. So for a bridge spanning a 5 metre gap, so that's going to be the span length. We need to find the deflection, which is y, when a point load is supported at the midpoint of the beam. So we know that we have, so for A, we are finding y, and we have the weight in kilonewtons is 2,000. We've got L is the span length, and that is 5 meters. So we've got 5 cubed over 48 times E, which was the Young's modulus, and then times by A, which is 1.33 times 10 to the minus 4. So on our calculator, we've got 2,000 times by 5 to the power of 3, and then on the bottom we have 48 times 2, 11 times 1.33 e to minus 4. So we've got 1.95, and we've got a to the power of minus 4. So to 3 significant figures, that is going to be 1.96 times 10 to the minus 4, and y we are measuring in meters, so that will be meters. Okay, right. So for a beam spanning 5 meters, find the point load. So we don't know W, supported at the midpoint of the beam to cause a deflection. So for B, we are still using our same equation, only this time we know our deflection, and we've got a deflection in the beam of 0.1 millimeters. So 0.1 millimeters, we times by 10 to turn it to centimeters, and times it by 100 to turn it into meters. No, we don't. We've got 0.1 millimeters, so we divide by 10 to turn it into centimeters, and then divide by 100 to turn it into meters. So we've got 1 times 10 to the minus 4, and that is our deflection. We've then got the point load that we don't know, and that is times by our 5 meter gap, which we do know.
Hiya. Do you have some...
So we are working still with the same E and A because it's the same beam. So we have 48 times by 2 times 10 to the 11 times 1.33 times 10 to the minus 4. Okay, so they are to a certain extent going to want us to rearrange it. So if we put in this bottom section here, we've got 48 times 2e11 times 1.33 e minus 4. And so this bottom section gives us this with a huge number of zeros. And so when we rearrange it, we'll multiply this by 1e minus 4. So we know that 127,680 is 3 cubed W, and so that's going to tell us that W, if we then divide by 5 cubed, which is 125, we should come up with 1021, and this is measured in kilonewtons. It is worth noticing that if you put this into graph and had it with the numbers that we know, so W is the thing we don't know, so that would be our value of x times 5 to the power of 3, and then divide that by 40. I probably ought to bracket that together. 48 times 2e11 times 1.33 e minus 4. So we are going to need a view window that goes up to about here. So if we put that up to 2000, and we are being asked about 0.1, so that can go from 0 up to 2. So if we do gsolve xcal, y is 0.1, only it's not 0.1, it's divide by 10 to be in centimetres, divide by 100 to be in millimetres, and then we should get a value here, and so you can just double check that you're right. Okay, so we are then looking at our distributed load, and that works in a slightly different way. Okay, so next we're looking at a supported beam with a uniformly distributed load, and it's got this equation here, and so if we're plotting it with L cubed, it will have this as its gradient. If you look at the question, however, what we are doing is we are looking at L to the power of 4. Now that's because of stuff that we're told on the data sheet. So we know that W equals 20. So we are told that span length is 10, then it will be 20 times 10. Span length is 8, it will be 20 times 8. So we know that W is going to be 20 times by L. So if we use the equation that we are given on our data sheet, which is y equals 5WL cubed over 384EA. If we substitute in this fact from this last two lines of our data sheet, we end up with y equals 5 times 20L times L cubed, and that is over 384EA. So if we combine these together, we've got 5 times 20 is 100, L times L cubed is L to the 4, and that's over 384EA. So that's why in this case where we've been given this equation. It is effectively the same thing. And we are also told that L, W and A are as above. So if we sketch a graph of y against L, this bit of sketch is actually sort of important. Things that we know it's going to be increasing, and we know it's going to go through the origin because we don't have a plus or a minus anything, and we know that it's going to be an L to the 4 graph. So from a sketch point of view, we've got y, we've got L. It's going to have to go through the origin, and then it's a positive to the power of 4 graph, so they come a little bit flatter than quadratic and go up. Realistically, looks a lot like a quadratic. Then when we're looking at 4 part D, because that one was 4C, use the equation to find the span supported by the beam, which gives a maximum deflection of 1 centimetre. So 1 centimetre is going to be our deflection, so 1 centimetre becomes 0.01 metres, and then we've got 100 L to the 4, and we are then using EA as it was at the beginning, so we have 384 times 2 times 10 to the power of 11 times 1.33 times 10 to the minus 4. Huge, massive fraction. So that gives us L to the 4 equals 102.1440. And so to undo to the power of 4, we have to use to the power of a quarter. So we have 102144 to the power of 1/4. That's because I didn't put over. Delete that and press the button I meant to. So we get 31.79. So L is going to be equal to 31.8. And L is our span length in meters.